Okay, so we're going to look at a handful of two-dimensional dynamics problems now that are going to involve forces and components. I call this the lawnmower problem, and it's just a problem, say, where we apply a force on an angle to an object. So it's kind of like pushing on the handle of a lawnmower. All right, so we start with the force diagram. Well, it's 50 kilograms, so obviously there's going to be weight here acting downwards. Um, there'll be a normal force pushing upwards from the ground. So the earth pulls down, the ground pushes up. We have an applied force here pushing along the handle. And then because the ground is rough, we also have friction. So let's just label those. So this is the normal force from the ground pushing up. This is the weight, and the weight of 50 kilograms, 50 times 9.8 will be 490 newtons. This is friction. And then this is just our applied force that we're applying along the handle. Now, key observation is that the normal force is not equal to the weight in this case. And I've drawn the arrows to scale. You can see it clearly. Now, why would the normal force be bigger than the weight? Let's think about that for a moment. Well, simply because this force that we're pushing with, we are partly pushing downwards. And therefore, we are squeezing the ground a little bit more, and the ground is going to react and push upwards with more force. So in the vertical direction, the normal force does not equal the weight. So if we call this the y-axis, and then if we analyze forces, as we usually do, in the x and y direction. Now, it's still true that there's no motion in the y direction, because a lawnmower doesn't lift off the ground. That tells us, as usual, that the acceleration is 0 and the net force is 0, or the forces balance. But because there's a third force here, this y component, let's call that the force component in the y direction. Because of that, Fn does not equal mg. So how do we set up that equation? Well, if force is balanced, then it must be that all the forces up have to equal all the forces down. The upwards force is the normal force. The downwards force, there's two. First of all, there's the y component, and then secondly, there's the weight. Now, how do we figure out what that y component is? Well, we're going to do a little trigonometry. This is 200 newtons of resultant force. This is a 20-degree angle along the handle. So this is the opposite side. This will be 200 sine 20 degrees. Okay, so 200 sine 20 is 68.4. So we're pushing down the handle with 68.4 newtons. And so the normal force ends up being 558.4 newtons. Now let's analyze forces in the horizontal direction. Well, we've got friction here that'll resist the sliding, but we also have a horizontal component to the right of the pushing force, and that's obviously what makes the lawnmower go. So I'll call that the x component, and I'll work it out down here just to not clutter the diagram. That's the adjacent side, so that's the cosine component, and that works out to 187.9 newtons of force to the right. Now we have friction to the left. Friction will be mu times the normal force. The mu constant is given as 0.1. So when we multiply by the normal force that we found previously, we find there's 55.8 newtons of friction. So now we can say there's an unbalanced force in the x or horizontal direction. This way is x. Unbalanced force is always equal to ma. In this case, the unbalanced force is the x horizontal component of applied force minus friction. So we have 187.9 minus 55.8 equals the mass times the acceleration. Solve for the acceleration. We get 2.64 meters per second squared. So really, we're just doing the same thing. We are drawing a force diagram, finding components, and applying Newton's second law. What's a little different here is we have an applied force that we have to resolve into components, and that the normal force does not equal the weight. Now, we can play around with this a little bit in the notebook software, and note that in the y direction, we can play around if the software will cooperate. There we go. In the y direction, the normal force does not equal the weight. Clearly it's a lot longer, but it does equal the sum of the weight and the y component, because the forces in that direction are balanced. Okay? Here's another question for you to try. You can pause the video and give this a try. First, complete the force diagram. The mass is on a ramp, and there's an extra pushing force on it, you're told. So complete the force diagram. I guess I should really move these over here, because that's the answer. So this is what you're supposed to start with in the workbook. So here's the applied force F. So draw the force diagram, and then complete the force equations. Okay, so hopefully you paused the video and took a crack at that. Let's complete it now together. The other forces on the block are, here we have the gravitational force. Here's the normal force perpendicular to the ramp. And then with no other forces acting horizontally, gravity is going to tend to make it slide down the ramp, so friction will be up the ramp. Let's label those now. Whoops, there we go. So here is Fn, force of friction, and gravity. And as we have done many times on the ramp, we are going to resolve gravity into components. This squeezes us onto the ramp, and this pulls us down the ramp. Now, we put it down here because that makes the triangle easier, and we learned that whatever the angle of the ramp, this is similar. This is the same angle. So this component here is what I call the squeeze component. That's the mg cos theta component. And this is the slide component. That is the mg sine theta component pulling us down the ramp. Now, if we think of the lawnmower problem that we just did, it's similar in that because of this force F, our usual equivalence between Fn and mg cos theta no longer holds. You could see that Fn is actually bigger than mg cos theta here. Why is that? Because of this extra downwards force F, and that is going to enter into the force equations. Now we'll use the usual coordinate system, the tilted coordinate system, where that's the y direction, and this is the x direction. So hopefully you took a crack at this and got something like this. In the y direction, the forces are again balanced because there's no motion. Forces are balanced. And we'll just introduce a bit of physics notation here, a slightly different way to write this. Instead of net force, we'll use sum notation. This means the sum of the forces in the y direction. Now, that's going to equal the mass times the y acceleration, which is 0. So this whole side is 0. So what forces are in the y direction? Well, we've got in the positive y direction, we've got normal force. In the negative y direction, downwards, we've got the applied force F, and we've got the squeeze, mg cosine theta, and I'm really running out of room there. So because those equal 0, we could take those two forces over to the other side and get this expression here. Now, in my sort of simpler approach to force equations, I just would have said up equals down in the y direction and arrive at exactly the same thing. This is just a slightly more sophisticated way of writing it. Now, in the x direction, there is again no motion, so again the forces have to balance, and we'll use that similar sum notation. So the sum of the forces in the x direction is always equal to the mass times the x acceleration. The x acceleration in this case is again 0 because there's no motion. What forces act in the x direction? There's just two. There's friction and the slide component. So they have to be equal to each other. mg sine theta is in the positive x direction along my positive x-axis, and friction is in my negative direction along the negative x-axis. So mg sine theta equals friction when I take this over to the other side. That's what the force equations look like. All right, here's another problem, another sort of 2D dynamics problem. And so we're told that we're pulling on this boat. Again, this is the answer, so I should pull this out of the way a bit. And there's a couple of forces acting on it. These are the gondoliers pulling the boat along. And I've drawn these force arrows a little longer just to give me more room because, yeah, no surprise, what we're going to do here is we're going to break those forces into components. And we see that both of these gondoliers are pulling they have components of force that are in the same direction. I guess we could call it horizontally, or we could call it along the x-axis. We will, as usual in this sort of problem, call this the x direction and this the y direction. So we're given that this is a 20-degree angle and that this is a 30-degree angle. And in both cases, those are adjacent components. And in both cases, they're positive. So this is going to be 150 cos 20 positive, and this is going to be 300 cos 30 positive. And so you would add those together to find the resultant x force. Now, in the up and down direction, these guys are working opposite each other. Here, let me make this look more up and down. There we go. This guy tends to pull the boat towards him, and so does this person as well. So those are going to cancel each other out. We see this one is in the positive y direction, and it being the opposite side, that will be a sine component. This will be 150 sine of 20 degrees. This one's in the negative y direction. It again is an opposite side. It'll be 300 sine 30. That's in the negative direction. So now, just as we did with vector addition earlier, we add to find the resultant x, and that gives us 400.8 newtons of force. Those add together. These partly cancel each other. The downwards one is bigger, so we end up, when you add those numbers together, with the downwards of 98.7 newtons. So what's the resultant of those two? Well, this is a triangle. These will be perpendicular to each other now. So it's just a Pythagoras. So this is 400.8 and this is 98.7. So we can now calculate that and find out what the resultant force is and the resultant angle. So just doing Pythagoras on those two components, we get a resultant force of 412.7 newtons. And then if we do a tangent ratio, don't worry about the minus sign, but tan theta being 98.7 over 400.8, we get an angle of 13.8 degrees, and that's a south of east angle. Now the problem actually asked us for the acceleration, but all we have to do then is just divide the force that we've got here by the mass, and the mass is 100. So just dividing this by 100 and answering to 3 sig figs, we get the acceleration of the boat. So there is an unbalanced force here in both what I called the x and what I called the y direction. So we expect this boat to sort of move not at 20 degrees or at 30 degrees, but we said about 13.8 degrees. Oh, below the horizontal, so it's kind of going to move this way. Now, another way to solve that problem is using triangles. We solved it here just by finding the components and adding them, as we did when we were adding vectors earlier on. This is almost a review question for us. But we saw that back when we did vector addition that we could add using the whole vector method. And so here's that first force vector. Here's the second one. And we add vectors head to tail. So we draw the first one and then draw the second one. And then this blue vector would be the resultant. And so you see it's sort of below the horizontal. Now this just ends up being triangle trig for us. If we remember this angle here was 20, right, this was 20 degrees above the horizontal. And so that means that up here, this is of course 70. This one here was 30 degrees below the horizontal. So that means this angle here is 60. So in the triangle, you have 70 and 60 are 130 degrees. And this was 150 newtons, and this was 300. So you could just do sine angle side. You could just use the cosine law. C squared is a squared plus b squared minus a squared plus b squared minus 2ab cosine c, and you would find this side, and it would exactly be the 413 newtons we found earlier. Okay, so that was a problem where we had acceleration. Now, and the acceleration was in both directions, so that was a little different from what we had done previously. Now we're going to deal with a problem that's at rest, not accelerating in either direction. That's called the static equilibrium problem. So here we've got, like a light that's held up by two wires, two cables. It's 10 kilogram light, so there would be a downwards force of gravity. And then one cable here, cable forces act along the cable. So this cable is going to be pulling to the left on this point. It'll be pulling out on the wall, but we don't care about that. We just care about the direction of this force. And again, forces act along cables. This cable will be pulling up and to the left. So there's the forces that act on this point. There's a downwards weight, and then there's two cable tensions. So mg, this will be 10 times 9.8. That'll be 98 newtons. And then there's two unknown tensions. I guess we'll call this the tension in the second cable, and this the tension in the first cable. Now, how will we proceed? Well, after we draw forces, we always apply Newton's second law, right, to the y and the x direction. And the y direction will just be straight up, as we usually do, and the x direction will be that way. Now, as is our habit, whenever we have forces and angles, we find components. So here we see that this cable is pulling partly up, and it's pulling partly to the left. And there's a 35-degree angle there. So this y component, the T1 y component, the upwards one, is going to be the adjacent side. So that'll be cosine. So that's T1 cosine 35. Let's analyze the forces in the y direction. Well, because this mass is at rest, the forces have to be balanced because there's no acceleration. So we'll go back and just use the simpler up equals down formulation, and then instead of summing the forces y. Now we see that on this mass, the only force up comes from this cable. It's a component from this cable. Abstractly, whatever T1 is, you're going to take cos 35 to find this upwards component. So algebraically, without a number, because we don't know T1, we have to say the upwards component's T1 cos 35. Now, we do know the downwards force, that's mg, that's 98 if you like, but we don't yet know what T1 is. Well, look, this equation will enable us to solve it here. Let me do that one a little neater. Let's get rid of that. Studies show students don't understand what that means sometimes. Okay, so now you see, hey, this y force equation is going to enable me to find T1. That's great. Let's also analyze forces in the x direction, because the forces are balanced here too, because it's not moving. So in the x direction, left forces will have to balance right forces. So what acts to the right? Well, the only right force is this cable pulling to the right. That's tension 2. How about to the left? Well, the force to the left comes from this cable pulling left. That's this component. So we're going to have to, again, use abstract trigonometry to get an expression for that. So the horizontal component, the amount of force to the right from this cable, is going to be T1 sine 35, because that's the opposite side of the triangle. Remember that although I draw it up here just to make the trig easier, of course, it's not going to let me grab that one. Oh, maybe it will now. Of course, the force really acts here and does indeed pull to the left. And so this one and this one have to be the same, but in opposite directions. And you'll see I've drawn it to scale, so they do indeed cancel each other out. If we were to, say, grab the weight here, we would see that, again, I've drawn it to scale, and it does cancel out that y component, the upwards pull of rope 1. Okay, so what equals T2? Well, we just showed above it was actually T1 sine 35. Now, these abstract force equations are sufficient to solve the problem. To solve for T1, you just take 98 and you're going to divide by the cosine of 35 degrees. Make sure you're in degrees mode. 98 over cosine 35, that's 119.6 newtons of tension in the first chord. Substitute that in here, multiply by sine 35, and you get, for tension 2, you get 68.6 newtons. Now, those abstract force equations, where we had to take an abstract expression for the components, enabled us to find the two tensions. Again, all we have to do is draw a force diagram and apply Newton's second law, and faithfully we'll be able to solve the problem. So we notice in terms of the whole vector that the tension in this chord ends up pretty big. It has to, because it has to balance this one to the right and this one downwards. If all three of those forces are balanced, then it must be that when we add the three forces together, we get nothing. We get a closed triangle or a zero resultant. So this tension 1 ends up being bigger than tension 2, and the weight, it ends up being the hypotenuse or resultant of those forces. So the static equilibrium problem is quite a common one in physics. And so we'll just try a couple of other examples. So for this one, here's our situation. Pause the video and draw the force diagram. Try that right now. Okay, so hopefully you were able to get the correct force diagram. We'll draw the forces for this point, sort of like the problem we just did. There'll be a downwards weight, and then there'll be two tensions, because there's two cables or ropes here. Forces act along the rope, so that one will be up and to the left. This one will be up and to the right. Okay, now pause the video. Well, I guess I'll label these first, right? We'll call that maybe tension 1, tension 2, and mg. With 120 kilograms, that ends up equaling 1176 newtons. Okay, now pause the video and think about what you're going to do next. Okay, so hopefully you realized that we're going to resolve these two forces into components. This one, T1, is partly up and it's partly to the left. This T2 force is partly up and partly to the right. Okay, so we need to find the components. So obviously with this 40-degree angle, we'll have sine T1 sine 40, T1 cos 40. Notice that the adjacent side here is a y component. So for T1, the components of T1, the cosine 40 is a y component. And in both cases, for T1 anyway, it's upwards y. For the sine 40, that's an x component, and it's in the negative x direction. For the components of T2, we've got T2 cos 10, the adjacent side, that's in the x direction, the positive x direction. And then we've got an upwards one here of T2 sine 10, sine because it's the opposite side. And we should put in the directions of those. So the T2 component is to the right in the positive x direction, and this is upwards in the positive y direction. Now we have gravity, that's in the downwards y direction, 1176. And so because these are at rest, we can write out the following force equations, because in the x direction, the forces have to add to 0, right? Or be balanced. So if we write the sum of the x forces, I guess we could do it this way, right? We could say that these two have to sum to 0, and those three have to sum to 0. So we'd be saying T2 cos of 10 degrees. Oh my goodness. What a mess. T2 cos 10 minus T1 sine 40 is 0. Or another way to put that is T2 cos 10 has to be the same as T1 sine 40. In the y direction, T1 cos 40 plus T2 sine 10 minus 1176 has to be 0. Or another way of putting it is the two upwards ones have to equal the downwards one. And the diagram was drawn to scale to illustrate that. So if we just flash back up there for a second, then we'll see that these two x components are just equal and opposite to each other. So T1 sine 40 and T2 cos 10 have to be equal. In the y direction, these two upwards components, when they're added together, are exactly equal to the weight. This, after all, is the condition to keep something at rest. The net force must be 0. So this diagram was drawn to scale to illustrate these relationships that we have down here below. Now these are abstract because you don't know what T1 is, so you can't work out the number. But we have faith that when we solve these equations, we'll get the correct answer. And in class, we'll talk about how to solve these equations, and we'll practice a little bit more with setting up force equations for a variety of 2D dynamics problems.